Welcome to General Equilibrium on NyQuil, Part 2, the household. I'm going to start this one off without too much of a fancy introduction where I talk about what we're going to do, because as you see what we're going to do, you're going to see and learn about what we're going to do. So what are we going to do? Well, we're going to start with optimization, and we're going to be doing so with the household. So a good way to kind of think about the way that this modeling is going to go: first, you have optimization. So that's where the households are optimizing, the firms are optimizing, the central bank would be optimizing. And then when everybody's optimized, right, then there's the equilibrium. And when we have the equilibrium, that's where we can, see all the cool behavior changes. If you tweak the equilibrium here, then what happens to this equilibrium over there, all that cool stuff. And then once we've done that, right, that's the first two parts of this are like the theoretical component. The third component would be like the empirical analysis. Daron Acemoglu goes through all of this with his principles of economics. But we're starting with the households optimizing. And what they're optimizing is their utility function. Now, they're maximizing their utility subject to a budget constraint. And once we've got this, we'll go to the firms. Firm behavior is a little bit different. It's getting its own separate video. But for this, we have a fairly simple setup, because households are going to have their utility function. There's a budget constraint that really constrains how much utility they can gain from market participation. What do I mean by that? Well, what I mean is there is some utility function which basically just says the household is just this endless pile of want, right? All that they want is stuff, and they want more stuff, right? Less is good, but more is way, way more betterer. But that constraint is what actually determines how much they buy. Because if you were unconstrained in your wants, you would just have like everything. And why wouldn't you? But that constraint, on the other hand, is sort of putting like an upper bound on how much you can actually consume. For example, we all want a giant house. Maybe we want a few fun, brand new cars, dry-aged fillets every night, right? There's all sorts of really nice stuff that we want. But sometimes we have to settle for like a nice enough apartment or a used car, or maybe, a new car just without all the fancy little bells and whistles that come with the one that we really wanted. And maybe we can't have fillets every night, so we got to go with like sirloins. Well, let's say you get a raise, right? You're doing really well at your job. Your boss is like, I like this person, so I'm going to give this person more responsibilities and a little bit more money. Well, maybe then you can afford a nicer house, or you could afford a nicer car or a few fillets. Maybe you can't get dry-aged fillets every night. Maybe that's only reserved for like Fridays and Saturdays, but, maybe you could have some more fillets throughout the week. Whatever. Stuff like that. Cool, right? Yeah. So you can see here this sort of the concept of this utility maximization. You have all these wants, endless wants, but there are resource constraints that are preventing you from actually being able to satisfy those endless wants. And we have preferences over things, right? Say in the steak department, you might prefer fillets over sirloins. I sure as hell do. You might prefer Porsche over Toyota. Maybe you prefer the Yankees over the Red Sox like I do. So we need a function that can describe that for us mathematically, that says, hey, I like this over that. This is cool, but this is more cooler. Toyotas are cool, but Porsches are more betterer. The Red Sox suck, and the Yankees are cool, right? And we get this function that can describe that for us mathematically. It's called a utility function. And what it does is it maps your abstract preferences, because these three things that I just listed over here, right? These are abstract preferences. And by abstract in this sense, what I mean is there's no like real value, like real number value that can be assigned to me making a statement such as I like fillets over sirloins, right? It's not like I'm like, oh, well, that's equal to the number 3. So I'm just going to think about the number 3 all day, right? And then liking Porsche over Toyota, well, that's pi. So cool. That's pi. It doesn't work that way, right? But if we can come up with a function that can map these abstract preferences to the real number line, then we get some kind of measure, and we can assign real values to these preferences over various consumption bundles. And the idea would be that the more you consume, the happier you are. But remember, in econ, there's always going to be a trade-off. So what is the trade-off here? Well, it's savings. Because you can either consume or you can save. If you have $1 to consume, if you've got $1 of income and you can either consume it or you can save it, you can't do both with it, right? So you either consume it or you'll save it. And whatever you don't consume, you save. So I'm going to denote consumption with a C subscript T. So C for consumption, T for, this time period. Savings is going to get S with a subscript T. And I'm going to define my utility function, U of CT, as the natural log of CT. So U of CT is like the abstract, kind of like f of x, right? And then the natural log is the function that is actually being performed on our variable C, where today's utility of today's consumption, CT, is given just by the natural logarithm of consumption. And this is what it would look like. So if I have units of consumption on the horizontal axis and utility on the vertical, so the left-hand side here, this would be utility, this is the vertical axis, and then this is the horizontal axis. If I were to plot that out, this is what it looks like. So the natural logarithm of C gives me this. So for all these various units of consumption, if I have 1 unit, 10 units, 20 units, 30 units, 40 units, I can, at any of these real positive values, I can assign some score of utility to that number of units of consumption. So when we look at this, we can see that it's increasing in consumption, right? Everywhere it is increasing in consumption. So if I go from, say, 1 unit to 2 units, my utility will increase. If I go from 20 units to 30 units, my utility increases. If I go from 40 units to 41 units, my utility will increase. Wherever I am, if I'm at the nth unit of consumption and I go to the n plus 1th unit of consumption, I will have higher utility. So it's increasing in consumption, but if you look, it's increasing at a decreasing rate. What do I mean by that? Well, if I go from 1 to 2 units of consumption, my utility is going to increase by a lot. But if I go from, say, 20 units to 21 units of consumption, my utility isn't going to go up by very much. So let's say I want to go from 1 unit of consumption here up to E units of consumption. Well, if I go from 1 unit of consumption, my utility is 0. To E units of consumption, it's 1. That's a really substantial increase in my utility. Whereas if I were to compare that to, say, going from 20 units of consumption to 30 units of consumption, my utility doesn't increase by anywhere near as much as it did from going from 1 unit of consumption up to E units of consumption. I did E because the natural log of E is equal to 1. So it's increasing in consumption, but it's increasing at a decreasing rate, which means you get happier the more you consume, but for each additional unit of consumption, that addition to happiness that you're getting isn't going to be as large as it was before. The idea would be, like, let's say you're homeless, and you go from not having a home to a 500 square foot studio apartment, you're going to go from miserable to, like, really, really happy, right? But if you go from a 500 square foot studio apartment up to an 1,100 square foot 2-bedroom apartment, you're going to be happier than you were with a studio, for sure, right? But the amount of happiness that you gain will be smaller than from being homeless and going to a small studio apartment. You know, maybe you've heard, if, say, you do live in a small studio apartment right now, you're like, God, I would love to have a 2-bedroom apartment. Someone goes, hey, it's better than being homeless. This is kind of what they're getting at, right? It's what's known as diminishing marginal utility. And mathematically, diminishing marginal utility means that the utility function has a positive first derivative and a negative second derivative. So the first derivative is positive, indicating that it is increasing everywhere. The negative second derivative means that while it is increasing, right, that's what the positive first derivative is giving us, it is increasing at a decreasing rate. So the first derivative of the utility function, called marginal utility, is this right here. The natural log of CT, right, the derivative of the natural log of CT is going to be 1 over CT. So marginal utility for this particular utility function is 1 over C. Now, if I wanted to get the second derivative of that, of the natural log of CT, I take the first derivative of marginal utility, right? So equation 2, if I just differentiate that, and I get this right here, negative 1 over C squared. So if you look, 1 over C is going to be greater than 0 for all positive inputs of consumption, but negative 1 over C squared is going to be negative for all positive inputs of consumption. So we have diminishing marginal utility, indicating the utility function is increasing at a decreasing rate. So this is what marginal utility looks like, right? Marginal utility is still positive because if you look at the vertical axis here, these are all positive values. If the first derivative is above 0, then it's positive. So we have a positive first derivative. However, if you were to take the derivative of this first derivative, right, you can see it's got a negative slope everywhere. So that would mean that the second derivative would be negative. And we can tell the second derivative is negative because every value of the second derivative is below 0. So positive first derivative, negative second derivative. Now, this is pretty much everything we need so far for a utility function in just one period. But what if we made this a 2-period utility function? Would we just add a CT plus 1? Maybe make it look like this? Sure, why not? I've got utility today, ln of CT, plus utility tomorrow, ln of CT plus 1. But are you as concerned about tomorrow as you are today? If you're worried about what you're going to be doing tomorrow, great. You know, we're always kind of planning ahead at least a little bit. You don't want to blow your entire paycheck today because, you know, you might need some of that for tomorrow before you get paid again. But if the bills aren't paid today, the lights aren't on tomorrow. So tomorrow's important, but it's not quite as important as making sure that you at least maintain some level of subsistence today. So we need to discount for the future. We have to consider the effects here of discounting. And we have to make the future matter just a little bit less than the present. Why are we going to do this? Well, if, like I said, you're planning for today and you're planning for tomorrow, tomorrow's not quite as important as today is. You still need to eat tomorrow, so you're going to have to plan to be able to eat tomorrow, but you need to make sure you're fed today. Otherwise, you're not going to be alive tomorrow to be able to eat. All right, so you're going to plan for today's meals, and then once that's taken care of, you start planning for tomorrow's. So let's say, just pulling a number out of my rear end here, tomorrow's 95% as important as today is. This is what we would have. I would have today's utility, natural log of CT, right here, plus tomorrow's utility, ln of CT plus 1, multiplied by 0.95, right? Before, here in equation 4, I was assuming that tomorrow was just as important as today is because it's the natural log of CT plus 1. Tomorrow's utility is being multiplied by 1. But here, it's multiplied by 0.95. So tomorrow's still important to us. It's just not as important as today is because you want to make sure you can still eat tomorrow. So you're not going to wait tomorrow with a 0. But you want to also make sure that you're being fed today first, right? Cover everything today to then be able to deal with tomorrow. Now, what if we don't want tomorrow to be weighted at 0.95? What if it needs to be something different? What if you want it to be weighted by 0.90? well, then this is what we would have. But maybe I want things to be a little bit more abstract than that. So instead of just multiplying it by this hard number that, okay, 0.90, and it's just that, or 0.95, and it's just that. Maybe we can have it where that discounting weight can be anything, as long as it's between 0 and 1. And then I can assign a variable to that weight. And so I'm going to call it beta, which is the discount factor. And our utility function of 2 periods in this case is going to look like this. So I've got the natural log of CT, which is today's consumption, or today's utility of consumption, plus tomorrow's, which is the natural log of CT plus 1 times beta, where beta can be anything in between 0 and 1, inclusive. So it can be 0, it can also be 1. Now, beta itself is actually a function. Beta is equal to 1 over 1 plus rho. Rho is what's known as the discount rate, and it's a measure of how patient you are. So beta is a measure of how much the future matters relative to today. Rho, that silly-looking p, is the discount rate, and it's a measure of how patient you are. If rho gets bigger, then you get more impatient, and the future matters less than the present does. So beta would thus fall. Why? Well, because fractions. If rho were to fall, then you get more patient. The future matters much more than it did previously, and beta would increase. So if beta increases, the future matters more. Now, I don't want to say necessarily the future matters more than the present because, well, it's always going to be discounted to at least as much as the present, but it's never going to be any more. But it becomes relatively more important than it was relative to a lower value of beta. So if beta increases, the future matters more. And if beta decreases, the future matters less. Now, nothing here says that the utility function can't go on further. Say, I want to do 3 periods. Cool. This is what I get. The natural log of CT plus beta times the natural log of CT plus 1 plus beta squared times the natural log of CT plus 2. Now, why would I have beta squared here rather than just beta? Well, the reason for that would be I need to make sure that the day after tomorrow, terrible movie, matters a little bit less than tomorrow. Because I can't just have today, which I value at 100% times natural log of CT, plus tomorrow, which is, say, 0.95, but then the day after that's also 0.95. Well, that doesn't make any sense because we want this to be consistent across time periods, right? So if we want it to be consistent across time periods, then I need to make sure the day after tomorrow is a little bit less important than tomorrow. So if I square it, it's going to be guaranteed to be a little bit less. Why? Because if you take the square of a number that's between 0 and 1, it's going to get a little bit smaller. 0.95 is going to be greater than 0.95 squared. If you don't believe me, get a calculator, work it out. I could do this over an infinite number of periods if I wanted to, and this is what I would get. I would get u of c equals the sum from t equals 0 to infinity of beta to the power of t times the natural log of CT. And if you were to write that out, the first 3 terms that you would get would be equal to this right here. Now, you would have an infinite number of terms after that, but the first 3 terms of this series that you would get would be these guys right here. Now, maybe we can learn how the infinite horizon stuff works a little bit later if you think it'll end up being easier for you. I've already got a video lecture in place. I just need to record the video lecture. It's something that if you want to watch it, feel free. Totally fine with doing that. If you want to just look at the 2 period, which is what I'm really going to be stressing for this course, stick with that, whichever one's easier. But in the graduate level macro, hardcore macro research, like, the stuff in academia, the stuff that central banks use, they use infinite horizons. We, however, will likely just be sticking with a 2 period problem. So we generally use an infinite number of time periods, but if we make a couple of simplifying assumptions, we can actually get just about as many of the valuable tidbits of information from a 2 period model that you can get from an infinite horizon model. Now, I've showed you this in the last video, but again, we can look at it. this is what the utility function would look like if it's graphed out in 2 periods. So this isn't the utility function over multiple units of consumption like what I've got, where were we? Here, right? This is utility U of C, right? Where just looking at how the utility function changes with respect to adding or taking away various units of consumption. No, what we've got here is the comparison between CT and CT plus 1 for any level of utility, right? So let's say if we go back for a second to this, right? If I want utility to be 1, right, I need E units of consumption. But that E units of consumption can be split up between CT and CT plus 1. Right? If, say, I've got 10 units of consumption, that's going to yield whatever this is here. I don't have a calculator in front of me, so I can't tell you exactly what the natural log of 10 is. But, you know, okay, it's a little bit greater than 2. So if I want utility to be equal to 2, or a little bit larger than 2, whatever that value is, then let's say this curve here is what we get when utility is equal to 2 point whatever it is. Well, I can have a lot more units of consumption of CT plus 1 and very little of CT, or I can have almost exclusively CT and very little CT plus 1. But any combination of CT and CT plus 1 will give me utility of 2 point whatever it is. But the utility function is only half of the stuff that we got to learn. The constraint's the other half. Now, the constraint is this. I kind of showed it to you already. Y equals C plus S. And it says that income can't be exceeded by the sum of consumption and savings. So whatever we save today is available for consumption tomorrow, plus a little bit of interest. Now, if we add in the second period, we'd want to make it look like this. YT plus 1 equals CT plus 1 plus ST plus 1. But what's the issue with this? Well, before we go any further, I will say this is for a 2-period model. So if we have a 2-period model, the world exists for today, it exists for tomorrow, and then it ceases to exist. So if I've got tomorrow's constraint of YT plus 1 equals CT plus 1 plus ST plus 1, what's the issue with that? I'll leave it here. I'll let you think about what the issue could be. Remember, 2-period model. So this equation 11 is the constraint for the first period. This is the constraint for the second period. So think about what that issue is. I'll leave it here. And in the next video, we can go over what the issue actually is. Thanks for watching, and there's another one coming shortly.